Dear students, in the last class we have to prove three results and then try to define the product HK, and then we have to, in the end, we say that under what condition we can say that HK is a subgroup. So this lecture we start with the theorem of this. When H and K are a subgroup of a G, then we try to show that Hk is a subgroup of a G if and only if Hk and Kh are same. So the last theorem result we have to discuss, that means is a much stronger result. This is saying that if H and K are two normal subgroups, and then we have to taking the intersection of these two is equal to identity, and we show that then every element of H is commute with the elements of a K and vice versa. So let's today we start the proof of this theorem, and this theorem is saying that let H and K be subgroups of a group G, and then Hk is a subgroup, and if and only if Hk is equal to Kh. So we just try to assume that Hk is equal to Kh. If Hk is the element of a Kh, then for some H is the element of H and K is the element of a K, then we can say that Hk is equal to H1 K1. Some H1 is the element of a H and K1 is the. So we take some elements of a H1 and we take some H1 and H into H comma H1 is the element of H, and K comma K1 is the element of a K. Then we can say that Hk is equal to H1 K1. Now to prove that Hk is a subgroup, then we have to show that Hk is a closed and each element of Hk has a inverse in Hk. So first we have to show that Hk is a closed. So you know that Hk is a closed. This condition you have given, and then we have to take any two elements of this Hk, and then we show that the composition of this is also belongs to this set, and also the inverse is also exists. So we just take two elements. Suppose x is the element of a Hk is the element of H, y is the element of H1, K1 is the element of Hk. Then we have to show that xy. So xy is equal to, we can write Hk H1 K, and now you just say that this we can write in the form of this H of K of H1 and then this because you have a K of H1 is the element of a KH, and you have a given KH is equal to, you have a H of K. So this means we can say that similarly K of H1 is the same as a some H2 K, and then if H2 K is there, for some H2 is the element of H, and we have a K2 is the element of a K. So we have to just write this H, K1 is the element of a KH, and this H is the element of HK, and then this can be written as a H2. So this can be written in the form of this means X, Y can be written as a H, KH1 is the same as we have a H2 and K2, and then we have a K1, and now you know that this is the H is the element of a H, and H1 H2 is the element of H. This means H2 is also the element of H, and K2 is the element of a K, and K1 is also the element of a K. So we can say that this simply we can say that K this is K2, K1 is also the element. So this is the element of a H, and this is the element of a K. This means this is the element of a HK, and then we have to take a X as, and X and Y are the element of HK. Then we have to show that X, Y is also the element of HK. So this means this is closed under the binary operation. Now we have to show that X is the element of this. The X inverse is also the element of a HK. So you have a X is equal to, you have a H of K, and then we calculate X inverse is equal to, we have a HK ka whole inverse. This can be written as a K inverse and H inverse, and now this is the element of a K of H, because you have a if K is the element of a, you have a K is the element of a K, So this implies that K inverse is also the element of a K, and you have a H is the element of H. It also implies that H inverse is also the element of a H, this element of H. So if this is the element of H, so this is the whole thing is element of the KH, and that KH is equal to, you have a HK. So this implies that this is, you have a K inverse, H inverse is the element of HK, and then this is nothing but is equal to this. So this implies back is equal to, you have to show that X inverse, we have to simply say that this X inverse is the element of a HK. So we find that if we take it any two arbitrary element x and y belongs to the HK, then we show that x, y is also belong to the HK, and if x is the element of HK, x inverse is also the element of HK. So we have to prove this clearly, and then we have to by inverse also, because this is the element of a using the property of a H and K, and then we can easily show that HK is a subgroup of a group of this is of G. Now conversely, we have a HK is a subgroup. We have a given HK is a, conversely, suppose that HK is a subgroup of a G, then we have to show that HK is the same as a KH. So if HK is a subgroup, then we can say that H is the element of H, K is the element of H, then HK H inverse K inverse is the element of H. Now you see this H inverse K inverse is the element of HK. So this means H inverse K inverse, inverse is also, because HK is a subgroup. So every element inverse is also inverse of that element is also belong to the this same set HK. So the inverse of this is equal to this. Now if inverse, you have to open this is simply this is a K inverse to inverse, then H inverse to inverse is also belongs to the H, then K inverse is equal to K, H inverse is equal to H. This is the element of a HK. So we can say that we take a some elements of this is also the element of HK, and now this is what, this is nothing but is equal to, we show that KH is the element of HK. This means we can say that KH is the element of HK, means we can say that KH is containing into the HK. So this means we can simply show that this thing is equal to this. Similarly, we can say that we have to take a K inverse, H inverse is the element of a KH, and then this can be written as a is this thing, then we have a K inverse, S inverse to the whole inverse is also the element of a KH. If open this, you can say that you have a H inverse to inverse, then you have a K inverse to inverse is also the element of a KH. Then this is nothing but is equal to HK is the element of a KH. So we can simply say that from here we can say that HK is containing into the KH. So we have a show that KH is containing into the HK and HK is containing to the K. So by these two conditions, we can simply say that HK is the same as a KH if HK is a subgroup of a group G. Now this completes the proof of this result. So now we have to write into this form. So clearly we can say that X is the element of HK, X inverse like into this form, and then we have to HK, and hence KH is equal to is the same is equal to this form. So we prove that this means this if the condition is this, we have if H and K are two subgroups, then HK is a subgroup if only if HK and KH are the commute. So if HK and KH are the same, left coset and right coset are the same, then only we can say that the product of H and K two subgroups is again is a subgroup. In general, HK is not a subgroup. HK is a subgroup only when HK and KH are the same. So now we have to just this result, this theorem. In this theorem, we can say that let G be a group and N is a subgroup of a G and K is a subgroup of a G. And now we have to say that if N is a normal in G and K is simply the subgroup of a G, then N intersection K is a normal in K. So we have a N and K. N is a normal subgroup and K is a ordinary subgroup. And if N is a normal in G and K is the only subgroup of a G, then N intersection K is a normal in K. If both N is normal in G, K is normal in G, then N intersection K is normal in G. If either N is normal in G or K is normal in G, then Nk is equal to Kh is normal in G. We can just say that if N is normal in G and K is normal in G, then Nk is normal in G. So we have to, this is the 4 parts, we have to try to prove one by one. We have take a 2 subgroups, N and K are the subgroup, and then first condition is saying that if N is a normal subgroup of a G and K is an ordinary any subgroup of a G, then we try to show that H intersection K is normal in K. So we take any X is the element of a H intersection K, and for any K is the element of a K, then we have a Kx K inverse belongs to the N, since N is a normal in G. Okay, since X is the element of N and this K belongs to this is N is a normal in G. So if N is a normal in G, then we can simply say that Kx K inverse is the element of a N, and then because also this Kx K inverse is the element of a K also, because X is the element of a K, so X is also the element of a K. So if X also element of a K, that means this element of a whole thing is element of a K. So this means since because we have a X is a subgroup of a G. So if we have a X is a subgroup of a G and X, we have to choose arbitrary element in the intersection of these two, and first we using the for any K belongs to the K, and N is a normal in G. So X K inverse is the element of a N, because K is the element of a K and K is clearly is a subgroup of a G. So this means there exists some element of a G which has satisfied this condition. So this is a normality. By normality we can say that Kx K inverse is the element of a N, and by the subgroupness we can say that Kx K inverse, because X is the element of this intersection, this means X is the element of N and X is the element of a K also. So this whole thing is also belongs to the K. So now what we show that the same Kx K inverse is the element of a N and Kx inverse the element of a K. So we just say that can say Kx K inverse is the element of a N intersection K for all X is the element of a N intersection K and K is the element of a K. Now we have to show that that means K X is the element of a this, and this K is the element of a K, that means clearly H intersection K is a normal to K. So this complete the proof of a this result. We can simply say that if we have to show that Kx, because this K is the element of a K and this X is the element of a N intersection K, so then we have to show that this N intersection K is nothing but is a normal to K. If we have a N is a normal to G and K is a subgroup of a G, then we have to show that N intersection K is normal to K. So this complete the proof of the part 1. Now the next part is saying that we have a, if both N and G are normal, N and K are normal, then Nk is a normal in G. So now we have to another condition is this: if we have a both N and K are a normal in G, so if N and since intersection of a subgroup is a subgroup clearly, so we can say that N intersection K is a subgroup of a G. Now we to try to show that this N intersection K is a normal to G, then there exists some element we have to take a G X, G inverse is the element of a we have to in N intersection K, where X is the element of a N intersection K and G is the element of a G. So we have to show that this property as H intersection K is a normal in G. So let's we take a consider a G and G inverse for all G, and then we have to consider this set for all G. We have to show that if we show that this is the element of a this G, then clearly this is a subgroup of a this. So we have to just study. So say this is means we have to take a G inverse be any element of a this set, and where A is the element of a intersection K. So we just assuming this G inverse, we take assuming that G inverse is the element of a G N intersection K and G inverse, and this A is the element of a this intersection. So clearly this we have to take A is the element of a this A is the element of a N intersection K. This implies that A is the element of N and this A is the element of a K also. So we just write into this form, if this A is the element of N, A is the element of a K also. So this means simply now G inverse, because we have a G is the element of a G, and then means clearly we can say that this is the element of a N, and also this is the element of a K. Why? Because N and K are the normal subgroups. So they are subgroups. So this means if A is the element of A intersection K, A is the element of N, so G inverse is the element of N, and G inverse is the element of a K, then we can say that G inverse is the element of a clearly is a element of a H intersection K. So we just show that G inverse is the element of a H intersection K. So we now this is the element of A intersection K, then G N intersection K, and then G inverse is containing into the N intersection K. And now this contained into the N intersection K, then by the equivalent conditions of a we have a normal subgroup where G is a N is a normal subgroup of a group G. When G and G inverse containing into the N, we can say that then this N is a if N is a normal subgroup of a G, then G and G inverse containing in N. If G and G inverse containing in N, then we also say that this G N is a normal subgroup. So the proof of this we have to taking the four equivalent conditions are there, and by these equivalent conditions we can say that if this containing into the G and G N intersection K, G inverse if containing into the N intersection K, so we can simply say that H intersection K is a normal subgroup by that equivalent conditions of a we have proved in the I think the first lecture of a normal subgroup. We have to try to prove the four equivalent conditions are there. If N is a subgroup, N is a first is N is a normal in G. If G and G inverse containing N, G and G inverse is equal to N, and then we have a Gn is equal to Ng. All these things are the equivalent condition. By this, so we have to show that G and G inverse containing N intersection K. So by that result, we can say that H N intersection K is a normal into G. So we have to prove that N intersection K is normal to G. So now we prove the B part also. Now the third part is saying that if we have a two conditions, if either N is a normal on G or K is normal on G, then Nk is equal to Kh is normal in G. So we have to say that Nk is equal to Kn. If N is a normal, either N is a normal of G or K is a normal of G, then Nk is equal to Kn is normal in G. So let's try to prove this third part also. We have to take suppose K is a normal in G. If K is a normal in G, so we have to then nk, small n and k for where n is the element of n and k is the element of a k. Now we show that this is the same as a knr. So because k is a normal in G, so there exists some n is the element of a G. We have nk is equal to k of n. By the again the that equivalent conditions of this, if k is a normal in G, then some elements of a G into k is the same as a G k h nk ng is equal to G of n. By that result, we can say that in the form. Now, if this is equal to this, means we can say that this nk is nothing but is equal to belongs to the nk, and nk is equal to kn. Then this is nk is the element of a kn. Then we have to nk is equal to nk, and then since kn is containing into the k of n, so nk is the element of a kn. If nk is the element of a nk, and we have to show that nk is the element of a kn, so this means we can show that nk contain into the k of n. So in place of a G and n element, we have to taking some n element of n is the element of a G, and this n is the where n is the nk is the element of nk. N is a normal. Then by use the normality condition, we have this thing is equal, and nk is nothing but is equal to is the element of n of k, and this means nk is nothing but is equal to a of n. Then nk is the element of a k of n. Then k of n, this is containing into this, so nk is the element of a k of n. Similarly, kn containing into the nk, and then we have to show that where nk is containing into the kn, and then similar we have to show that kn containing to nk. So nk is equal to kn, and since h is a subgroup of G and k is a subgroup of a G, and nk is equal to kn, hence nk is a subgroup of a G by that theorem. We just said that if H is a subgroup, just we have to prove the theorem. We can say that if H is a subgroup of a G, K is a subgroup, N is a subgroup of H, K is a subgroup of a G, then we prove that Hk is a subgroup if and only if Hk is equal to Kh. So Hk is equal to subgroup, K is a subgroup, then we have to here is a Nk is equal to Nk is equal to Kn. So it means by that theorem we can say that if we have two subgroups, then these are two product of these two subgroups is only subgroup when Hk is equal to Kh. So by Nk is equal to Kn, so this means Nk is a subgroup of a G. By using this theorem, we can easily say that by this is satisfy these conditions. So we prove that this is equal to clearly Hk is equal to subgroup. Now we have to show that the similar argument we can if n is a normal in G. If we taking first case, we have to divide this is the two case. One is n is a normal in G, another is a n is k is a normal in G. Another case is a we have a n is a normal in G. So this similar we can prove that the similar argument using this, and we have to show that similarly we can say that nk is equal to kn, and then we have to prove that by again this nk is a subgroup. So this complete the proof of this part of C. Now we try to prove the D part, and D part is saying that you have a both are subgroups are normal. If we have a say that this form, if both H and N is a normal in G, K is normal in G, then Nk is a normal in G. Then we can say that we can easily, you remember previously we showed that N is normal in G, K is normal in G, then Nk is equal to Kh for, but there is a condition in imposing in intersection is identity. So let's prove the last part of this theorem. That part is equal to, we have to, okay, so we have this. Now to show that nk is a normal in G, let G is the n element of a G, then G and G inverse containing into the n, and G, K, J inverse containing into the K, since n and K are a normal. Same we have a G is the element of a G, then n is a normal, so G and G we have n is a normal in G and k is also is normal in G. So if n is a normal in G, then G and G inverse satisfy this condition. If k is a normal in G, then J inverse is containing in the k. Again, that equivalent conditions. Now we have to show that this we have to take a G of n k G inverse, and this can be written as a G of n, and we have to write, because nk is written in the form of a like this. We can write, this can be written as a we put n k and then this is equal to identity element. So this is G of n, G inverse Gk, and the G inverse, and now we have to apply the associativity G and G inverse and G and k inverse. That is the element of a n, this is the element of a k, this means whole is the element of a nk, and this is the element subset of nk. Then clearly we can show that G of nk is containing into the nk, and again by this equivalent conditions we can say that nk is normal in G. So we have to prove that this result is also true whenever we have a n and k both are normal subgroup of a G, then we can say that nk is also a normal subgroup of a G. So these are all the equivalence conditions we have to proving this. So this means we can simply say that if we have a two subgroups, we have to, these are the conditions we have to proving is equivalent conditions, that we have a solve all this problem. So this conclude the all the important properties of a normal subgroups. We have to discuss various theorems of a normal subgroups, and some important properties of a normal subgroups. And so this complete the theoretical part. In the next class I will discuss some problems related to the normal subgroups, and then we have, after completing this normal subgroups, we try to discuss the quotient group, or we can say that is a factor group. So this complete the all the theoretical parts of the this normal subgroup. So thank you very much for this class.